How does a squid work in quantum magnetometry? Imagine a device so sensitive it can detect magnetic fields thousands of times weaker than what a compass can sense. That's what a superconducting quantum interference device, or SQUID, can do in quantum magnetometry. This technology is at the forefront of measuring tiny magnetic signals with incredible precision. A SQUID is made from a loop of superconducting material, which means it conducts electricity without resistance when cooled to very low temperatures. Inside this loop are one or more weak links called Josephson junctions. These junctions are thin barriers where superconducting electrons can tunnel through, creating a special quantum connection. These junctions are what make the SQUID so sensitive to magnetic flux, which is the measure of magnetic field passing through an area. When you apply a magnetic field to the SQUID, it causes a change in the magnetic flux passing through the superconducting loop. This change induces a tiny current called a screening current in the loop. The SQUID detects this current because it affects the behavior of the Josephson junctions. Specifically, the current causes a shift in the voltage across the device, which can be measured very accurately. In a direct current or DC SQUID, there are two Josephson junctions arranged in parallel. When the magnetic flux through the loop reaches a specific value, called half a flux quantum, the junctions switch from superconducting to normal state temporarily. This switching allows magnetic flux to enter or leave the loop. The voltage across the SQUID then varies periodically with the magnetic flux, meaning it repeats every time the flux increases by half a flux quantum. This periodic response makes it possible to measure magnetic fields with extraordinary precision. The other type, the radio frequency or RF SQUID, has a single Josephson junction and is often used in different applications. But the DC SQUID is more common because it offers higher sensitivity and stability. It can detect magnetic fields as weak as a few femtoslas, which is a quadrillionth of a Tesla. In practical use, SQUIDs are often calibrated with known magnetic samples. The device is connected to a superconducting coil that picks up the magnetic flux from the sample. The flux is converted into a voltage signal, which is amplified and analyzed. This process allows scientists to determine the magnetic properties of materials with great accuracy. In the realm of emerging quantum technologies, SQUIDs are vital for quantum sensing and metrology. They help researchers explore new materials, improve medical imaging techniques like magnetic resonance imaging, and even contribute to the development of quantum computers. Their ability to measure extremely weak magnetic fields makes them indispensable tools in pushing the boundaries of what we can observe and understand about the magnetic world around us.